Hello everyone, welcome back our class. We continue discuss the chapter 7, the state function of practical gas. The section 2, compression factor. When a gas does not satisfy the conditions of perfect gas, the gas state equation should be modified. Simplest way is to define a compression factor through perfect gas equation. Just as we can order Z equals PV over RGT. Certainly, if the gas is ideal gas, here the Z certainly equals 1. From perfect gas equation, we obtained V ideal equals Rg over P. Here is the ideal gas volume, specific volume. So the factor can be written as Z equals V over V ideal. Just the perfect gas, the specific volume, over the ideal gas, the specific volume, just is the compression factor. It indicates the compression factor is the ratio of practical gas specific volume with perfect gas specific volume at the same temperature. Okay, the practical compression factor of Van der Waals equation. The last several pages, we know we can use the Van der Waals equation at practical point. So here we can obtain ideal, we can obtain number, just the critical compression factor at the critical point. We can calculate the Z. C means critical point. PC VC over RTC just is 0.375. Tell us Van der Waals equation for all substance has the same critical compression factor for any substance. Here is just the Van der Waals equation tell us. However, the different gas we can find in for different substance. We find different gas has the different quantity, the compression factor. Generally is in 0.27 to 0.33 becomes smaller. It's not 0.375 becomes smaller. The compression factor for real gas, the factor becomes smaller. The section 3, we will study the Virial equation. The compression factor usually is expanded into power series by V1 over V or P. So this way to separate, to expand the compression factor. We know Z equals PV over RGT, but Z is a function of V or P. So in this section, we just expand the compression factor by 1 over V or P. We obtained Z equals 1 plus B over V and C over V power second and D over V power third. All Z equals 1 plus BT plus CP power second plus DP power third. So here B, C, D or B prime, C prime, and D prime is a function of temperature. I called second, third, fourth Virial coefficient. So it is a series by 1 over V or P. This equation, we can call it Virial equation. Virial equation. For pure substance, Virial coefficients are only the function of temperature. For definite gas, they are only the single valued function of temperature. No relationship with pressure, with volume. Just is the function of temperature. Also, they can be measured by experiments. For low or middle pressure gas, truncated type Virial equation can be used, because Virial equation maybe so many terms is very difficult to calculate. So most case we can use their truncated type Virial equation. Sometimes 2 terms, 3 terms Virial equation. So become simple Virial equation. Okay, section 4, some special equation of state. Until now, we have learned van der Waals equation, Virial equation. So these 2 real gas equation certainly cannot satisfy our requirement. So from the industrial field, we can obtain some special equation of state for real gas. Different real gas may be different special equation of state. For some chemical gas or low temperature gas, we can consider the special equations as follows. The first famous equation is Redlich-Kwong equation, very famous. It is a modified van der Waals equation. P equals RT over V minus B is the first term. The second term is minus A over T power 0.5 times V also times V plus B. It is a very good equation for chemical gas. Here, the constant A and B we can obtain from the experiment. But this equation cannot be used to calculate various saturation steam. When the gas is saturation, steam cannot be used. Okay, the second very good real gas equation is Redlich-Kwong equation. It is a modified Redlich-Kwong equation. It uses temperature function A function T to replace A over T power 0.05. Here the A is a function. It is not a constant. Here we can order A T function equals ATC alpha T. So here alpha T is a dimensional temperature function. It is a still function for temperature. So different temperature we can obtain different alpha. This equation can predict accurately saturated vapor pressure of light hydrocarbons. We can obtain very good the result accurately. The third one is Benedict-Weber-Robbin equation. Benedict-Weber-Robbin equation can be used to nearby liquid phase region. This equation is very long. many terms, very long terms. 8 empiric constants A0, B0, C0, A, B, C, alpha, gamma can be obtained from experimental data. Different gas has the different quantity. Even if the pressure is higher than 2 times critical pressure, the area is still very small. Maybe only 1%. 1% is very good. Martin-Hall equation also, this equation is very complex. Many terms. But we can tell you where the K equals 5.475. This equation including 9 constants in the equation. Many constants. However, the constants can be obtained from critical parameters. The equation for common gas usually only has 1% area. So the result is very good. But the calculation process is very difficult. Okay, thank you.